just to briefly go over distance, displacement, speed, velocity, and acceleration, which this is the main stuff we've gone over so far in Unit 2 in regards to motion. So first of all, when we're talking about distance, we are just talking about the total amount of ground you cover pretty much. So think of, we have a car, all right, and it travels 3 meters north, and then it travels, let's say 5 meters to the east, or someone walking, we can say. In terms of their distance, we would just add up 3 and 5 because they traveled 3, then they traveled 5. So as far as distance goes, they would have traveled a total of 8 meters, and that is your distance. Displacement, though, this is an interesting one. So we're talking about basically where we are in reference to where we started. So we think of this as your starting reference point. Okay, and then this right here in this case, this would be the ending point. So basically what we need to find is, what is this distance right here, okay? So this is going to be a more complicated problem. They're not all going to be like this. I'll show you some other ones. But in this case, we can't just add anything up to find this. We have to use, since it's forming this triangle, we can use the Pythagorean theorem. So to do that, we can abbreviate this side of the triangle as A, this side's B. So the Pythagorean theorem says that A squared plus B squared equals C squared. So this is C, and if we plug in those numbers, 3 squared plus 5 squared equals C squared. So 9 plus 25 equals C squared. And I'm not your math teacher, so I'm gonna type it in here. It's 9, and then the square root of 34 ends up being 5.8. So like I said, what I did here was 34 equals C squared. Then you find your square root, which then 5.8-ish. It's a decimal, but that's fine. So our change in X, or our change in distance, or our displacement, would be 5.8 meters. Okay, so that's one of the more complicated ways that we can look at displacement. Another way, you are starting right here, and you walk north, okay? You go to the store side, and then you walk the same exact path back. It's a little drawn over, but same path. Say this is 100 meters, and then this is 70 meters. And you stop here and you talk to your friend, okay? So this is where you started, this is where you ended. If I walked 100 meters, but then came back 70, I want to find what this distance is. So again, I drew it over, but think of it as being right on top of each other. So in this case, we would just do 100 minus 70. So this distance, or our displacement, is 30 meters. So she's 30 meters north, because she's up, so 30 meters north of where she started. But her distance, her total distance, would be 100 plus 70, because she traveled 100 and then she traveled 70. So her distance is 170 meters. Also in this example up here, if he traveled north and then traveled east, his displacement would be 5.8 meters northeast. Okay, so we want to make sure we include that direction also in our answer. And then one last example of displacement I can show you. Say you walk 2 miles this way, 3 miles this way, and 2 miles back. This is 2 miles, this is 3 miles-ish, and 2 miles. So 2 miles north, 3 miles east, 2 miles south. Okay, so this is where you started, and this is where you ended. As far as north and south go, our starting point and our ending point are the same spot. She went 2 miles north and then 2 miles back south, so we're good there. The only difference is this this horizontal difference. So in this case, we would say that our displacement is 3 miles east of where she started. And then to find her distance, you would just do 2 plus 3 plus 2, because in total, that is what she traveled. And then let's talk about speed and velocity. So speed, we are looking at the change in distance in a certain amount of time. And to calculate that, it is distance divided by time. And we can abbreviate this as a lowercase s. Velocity is the same exact equation. Distance over time. We're looking at the same thing. The only difference with velocity is that we include direction. Okay, so if we calculate speed, all we need to do is we might get 3 meters per second. If we were doing velocity, the question asks for velocity, we would need to say 3 meters per second south, or 3 meters per second upwards, 3 meters per second northeast, because it includes a direction. We want to know where we're going when we're talking about velocity. And then, so an example of this, let's say, what is the velocity of a car that traveled, let's say 30 miles in, let's just say 25 minutes. Okay. One thing that, say the question is asking, what is the velocity in miles per hour? So this gives it to us in minutes. We're gonna have to do a little conversion, but that's okay. We learned that in the last unit. So 25 minutes, that conversion factor to go from minutes, if we want to go to hours, well, there's 60 minutes in 1 hour. We're out of minutes. So then we just do 25 divided by 60. And we get 0.4 hours. Okay, so then to find our velocity, also let's say he's going from New York to California. The question would have told you that. So velocity equals distance over time. So 30 miles in the time we just converted, 0.4 hours. So 30 divided by 0.4 equals, so this person is going 75 miles per hour, and think New York to California, so they are going west. Okay, this is important because we're solving for velocity. All right, and then just to go over acceleration real quick. I'm actually going to do this on a different sheet of paper. All right. So as far as acceleration goes, acceleration is looking at the change in velocity over time. Okay, so we want to look at the change in our velocity over time. So our equation is A equals our final velocity abbreviated as VF, minus our initial velocity, VI, divided by the amount of time. So, say we want to know what the acceleration of a car is that goes from 30 miles an hour to, let's just say 80. And that happens in, let's just say 0.15 hours. I think we're talking hours, so might make sense. We'll see. So I said we're going from this to this. So this is our final. Our acceleration would be 80 minus 30 divided by 0.15. And to do that, let's see, 80 minus 30 is 50 divided by 0.15. So this person is going pretty fast. They're accelerating at 333 miles per hour squared. So this is our unit. When we're doing acceleration, we're measuring miles per hour squared, meters per second squared. It doesn't matter what units we're talking about, but we do want to square time. When we are just talking about velocity though, it's just miles per hour. And then up here with distance, we're just doing our distance measurement. So whether it's meters, miles, feet, we're just talking about length. So hopefully this helps you understand these a little better. It's basically just plugging into your equations and solving for variables. But if you have any other questions, please just let me know. Shoot me an email or a message and remind, and I'd be happy to help.
Hi, I'm Dr. Shanice O'Mara, and I hear you want to learn physics. I have to say, good choice. Physics is the science of how the world, really the whole universe, works. And I don't know if you've noticed, but the world I live in, things tend to move around a lot. So that's what we're going to study first, the science of motion. And it turns out to be incredibly useful for figuring out things like where you are, where you've been, or how you're moving through the world. Why is that worth knowing? Well, for one thing, the police use physics to decide exactly how fast you're moving through the world, and if that motion happens to break the law. So if you're going to understand how and why you got that ticket they gave you, and maybe even know enough to dispute it, you have to know the science of motion too. And in order to do that, you'll need to understand a few essential conditions that describe your physical place in the universe. Conditions like time, position, velocity, and acceleration. So to talk about all of these things at the same time, you'll need a set of equations that links all of them together. These are called the kinematic equations. So for the next few minutes, let's talk about how you can figure out your place in the world, literally, which just might help you beat that speeding ticket. Straight stretch of highway. Let's say you're driving on a straight stretch of highway, say someplace nice and flat, on the wide open spaces of the northern plains of the United States, say North Dakota. You come across a red light, and even though there are no cars in sight, you stop, because you're a good driver who obeys traffic laws. Then the light turns green, so you hit the gas, and exactly 7 seconds later, you hear the sirens and see the flashing lights of a police car. You're promptly served with a ticket for speeding in a 100-kilometer-an-hour zone. But wait, were you really going that fast? Did you actually break the law? You can't really tell because the speedometer in your car is broken. So you need to find another way to figure out how fast you were going and decide if you want to take this up with Johnny Law in court. That's where physics comes in. The physics of moving in a straight line. Let's start by talking about how your car was moving. Driving along a straight highway is an example of one-dimensional motion because the car can only move back and forth along that line. That's the difference from something that's free to move in all 3 dimensions, like a boomerang flying through the air. And instead of describing that motion just in terms of speed or direction like a police officer or other non-physicists might do, we physicists describe it with math. Maths that measures the 4 main conditions of the car's movement. It's time, position, velocity, and acceleration. Time simply tells you Change in position, known as displacement, is positive, you'll know you've moved in one of those directions. If it's negative, you're travelling the other way. But which direction is positive and which is negative? That's totally arbitrary. You could decide that east should be positive and west negative, or the other way round. But the answers you get will mean the same thing. You just have to make sure to keep track of which direction is positive and keep that in mind when you're talking about velocity and acceleration too. Velocity is the way your position changes over time, and it's also a pretty big deal. It's kind of like speed, but just like with displacement, it also tells you which direction you're moving in based on whether it's positive or negative. Now, what about when your velocity changes? That's the fourth quality of movement you'll want to pay attention to. Acceleration. If you've ever been in a car when someone slammed on the gas, that feeling of being pressed back against your seat is acceleration. Your velocity is changing. So how do we plot out all of these different conditions that describe the movement of you and your vehicle through the plains of North Dakota? A non-physicist might visualize this movement on something like a map, but for us, graphs are the most useful way to show how all this change in position is happening. Graphs are generally presented as position versus time, with position on the vertical axis and time on the horizontal axis. We'll label your position as X and time as T. Now let's imagine 3 different scenarios for how you drove through this small town and graph each one. First, let's say that after you went through the red light, you just stayed in one spot, say at 4 meters from the light, for 3 seconds. From that moment, the graph of your position would just be a flat line at x equals 4 meters, like this. Now what if you didn't stop, but instead were coasting at 1 meter per second? Then the line would be diagonal to show how your position was changing, like this. And the third time, let's say you were standing still at first at the 4 meter mark, but then you hit the gas. And you moved in such a way that after 1 second you went 1 meter in the positive direction, and after 2 seconds you went 4 meters, and after 3 seconds you've gone 9 meters. In that case, you end up with a graph that's all curvy like this. But there's more going on in these scenarios than just your position and time. You also have to be able to graph your velocity and acceleration. So to graph your velocity, you'd put your velocity on the